This video focuses on populating response curves and introduces some of the features and options in the DSS to facilitate this. So the populating of response curves takes place under knowledge capture, which is one of the three sections of the DSS and can be accessed along the top here. We click on knowledge capture and go to the response curves submodule. There are several submodules within the submodule: habitat and biota, socioeconomics, and export and import. We're going to be talking about the habitat and biota submodule. The socioeconomic module is almost identical to the habitat and biota submodule, but is for socioeconomics rather than the biophysical aspects of the system. And export and input is for importing or exporting information to or from the DSS. So let's go to habitat and biota. And let's go to site 2 and let's work on fish. Depending on what you have in your DSS, how many links you have, whether your response curves are populated, how many scenarios, how much hydrology you have entered, it can take quite some time for this section to open. So if you know that you are dealing with a big data set behind your DSS, then just wait a little while. It takes a while to enter. When the habitat and biota pages come up for your required site, discipline and species, it will look something like this. This is a very simplified version thereof. What this says is that fish species 1 is linked to the dry season minimum 5-day discharge and the wet season duration. These links have been made in the setup part of the DSS under the indicators links submodule. If those links have been made there, they will show up on your habitat and biota page as you open up. It's worthwhile at this point just checking that your seasons are correct, because those will affect the shape of your response curve and they will affect how your response curve reacts. And they will affect the reaction of the DSS to a particular flow regime. So as a general rule of thumb, if the link is to a flow indicator, then it should be linked to the same season. So in this case, these are both correct. Dry season minimum 5-day discharge to the dry season, wet season duration to the flood season. Right, so when the page opens, there's a couple of key parts to the entire page. First of all, we can get rid of that to give us a bit more space on the page. Let's start up at the top here. So right up at the very top, you've got the name of whatever species you are working on. In this case, I've changed the name of the species just to read fish species 1 so that the focus is not on the particulars of the indicator. And then there's a mean and a median value that are given here. These two values refer to this graph here, the big graph along the top, which is an integration of any results of the linked indicators down this side. So this is an integration for the baseline hydrological scenario, or hydraulic scenario in this particular case, hydrological scenario, that has been entered as the driving indicator to the DSS. These two here are the min and the max also of this particular curve. These become quite useful and very important a little bit later on. And then what we've got just under them are a whole set of modifiers. It is important to make sure that you set your modifiers before you start working with your response curves. So let's do that now. There's a little button here that says Show Modifier Hints, which is fairly useful with helping with the modifiers because they can be confusing at times. And what it does is, as you move your mouse over each of the modifiers, it will explain to you what each of them does. Okay, I'm going to switch this off while I explain to you because it tends to cover the screen. So let's start with dependence on the previous year. Essentially what this means is, to what extent does the indicator that you are now concentrating on, fish species 1, to what extent does the population in year 2 depend on the population in year 1? And essentially what this would mean is that if you have a species that is long-lived and produces very few young, you would expect that the population year on year is quite dependent on what happened the year before, because they're the same individuals, or the same individuals plus relatively few offspring being added to the pool. If, on the other hand, you are something like a mosquito, where your indicator is short-lived and can produce an enormous number of young, then you would expect that the population in year 2 is not necessarily dependent on the population in year 1. It's more dependent on the conditions that it finds in year 2. Similarly, a bird species that can migrate, something like a flamingo, for instance, that will come to a pan or a river when water arrives. But if water doesn't arrive, it's not there. So the population at that site or at that river is not dependent on whether there were flamingos there last year or not. It's relatively independent of this. So the fish species that we're dealing with here is one that is relatively long-lived and does not produce a large number of young. So we're going to make this dependence fairly high, around 70%. Why 70%? Because it does lay eggs, and if there's a drop-off in the population in year 1, and conditions are favorable in year 2, then the eggs that are laid there will hatch fairly successfully, the fingerlings and fry will have plenty to eat, and the population at the end of year 2 will be quite a bit bigger than year 1, based on what is happening in year 2. So essentially what this is saying is, how much does the population at the end of year 2 depend on the population at the end of year 1? So we've set that fairly high. The next one, let's just put the modifiers on so we can see what it is. It says, how long would it take for the curves to return to median from a 5% of baseline, so in other words, from a very low value in the baseline, if all the conditions were at median? Okay, so let's just say this in a slightly different way. If, for some reason, your population were to collapse and it's sitting at 5% down here, all right, of this particular fish species, for whatever reason, let's say that the river dried up for the whole of year 1, and there was a very small percentage of the population managed to eke out survival in a pool. Then year 2 comes along and everything goes back to median. It's not a better year than median, and it's not a worse year than median, but everything's round about the median conditions in that system. In other words, the wet season flows come down, the floods are pretty much what you would expect them to be, the duration of the season is what you would expect them to be under baseline conditions, the dry season flows are what you would expect them to be. So if those conditions returned and found, for some reason, a population of fish species 1 that was at 5%, how long would it take for that population under median conditions to get back to median values? The sorts of things that a specialist would need to consider here are similar to those that were considered for the dependence on the previous year. So they're the life history traits of the particular indicator. So let's look at fish species 1. If it's down to 5%, then this is a species that just now I said is fairly long-lived and produces a small number of young. All right, so it's not going to immediately shoot back up to median conditions if the conditions return to being favorable. It's going to have a little bit of time that it takes to get there. The time that it takes to get there is going to be dependent on how many young it has, how long they take to get to maturity so that they can have young. So let's say for this species, it produces 4 young that will survive the year. They then produce 4 young and so on and so forth, which means it'll take about 5 years to get back to median conditions, should it be at very low levels and conditions come back. The next modifier is similarly but going in the opposite direction. So it's a decrease if you had 200% of your median populations because conditions have been really, really good and conditions return to median. How long would that fish take to get back to median condition? Would it all collapse immediately, or would it do slightly better and slowly the numbers fall down? Again, this is a fish that is fairly long-lived, so it is going to decline if there's a drop in conditions, but not necessarily precipitously. So let's say that's 5 years as well. The next two here that have got these modifier hints coming up are fairly simple. They say what is the minimum and the maximum percentage that the population could get to. So if you're something that is very big, like a crocodile, then you would imagine that if conditions are really poor, and you can be eliminated from the system. And if you're eliminated from the system, it does not matter if conditions come back to being good a bit later on, because unless you are reintroduced to the system, it's extant from that system. So then the minimum that you can get to would be 0. If, however, you are something like a mosquito and conditions are really, really poor, there's a chance that even though there's driving forces pushing your population down, that you are not going to end up with 0. So you might have a residual population that's 5 or 10 or whatever percent. In this particular case here, the species, we said long-lived, not very many young. It can clearly be exterminated from a system. It can become extant in a system, so the minimum of the baseline is 0. The other side of that is, if conditions are really, really good, how much bigger can the population get? And this would really depend on what the conditions of the system are like at the time that you are studying it, the baseline conditions. Because if the population has been depressed for whatever reason, poaching or bad flow rate management, whatever, and it has been depressed, then clearly there's some chance for it to go up. But if it's a pristine situation where there's nothing that has affected it, it's unlikely that that population is going to go up to 500 or 600% of what it is if it's a long-lived fish. Okay, so we normally set that just at about 200%. Once you set those two, you don't need to worry about increase from very low. Essentially what it's saying is that if you do go down to extremely low values, what is the chances of you coming back up quite quickly? In the case of a long-lived fish, 0. Then we've got some upper and lower limit modifiers. These are essentially the density-dependent equations and are useful particularly in situations where you've got floodplain grazers or whatever, they're classic dependence curves. So essentially what they're asking is, if abundance is high, the degree to which the rate of increase will be slowed down as you go up in things like population pressures for resources start to take place, competition, so on and so forth. And similarly, as you start dropping down, at what point do you start to slow down? Usually in drift, unless there's a known density-dependent relationship, then we don't worry about those and we switch them off just to get rid of those hints again. Okay. And then the last one here, which is the lag period, is fairly obvious. And that is, if you have a change, how long will it take to be felt? Okay, so if you're something like a baobab tree and the flows in the system decline, you've got very deep roots, you can reach the water table very low, but there's no floods around to spread your seeds, it's dry on the surface, so the young plants when they first start growing can't reach down to the water and they will tend to die. So the old tree can carry on for a long time, but it's not producing young. So sooner or later, it will die. In the case of the baobab tree, that might be 100 years. But in the case of some other plant species, it might be much, much shorter, 1 to 2 years. In the case of our fish, this is an animal that is long-lived, doesn't produce very many young, so you can expect a slight lag period. If there's a failure of breeding season for 1 year, probably not going to affect the population overall. So for this particular fish species, we're going to put 2. I think it's becoming quite clear as I go through these modifiers, and it will certainly become clear as we move on into the response curves, that these curves cannot be filled in by just anybody. You need to know your species. You need to know the literature that surrounds your species. You need to know their habits. You need to know their life histories, all aspects of them quite well in order to fill in these curves. And this is where the time is spent getting drift correct, particularly in instances where you don't have a lot of data on which to rely. So I think that's, as I say, is becoming obvious as we go through. Okay, so those are the modifiers now. They're all filled in. So let's move to the other part of the habitat and biota response curve page. Okay, so what we've said is that these 2 here are the linked indicators. Next to them, there's these little graphs, and these will become the response curves. They will show the relationships that are entered here. On the right-hand side, each response curve has got a graph that goes with it and a place in which you can write whatever you need to write into it. Let's just talk about a graph for the second. So this pinkish line, it's actually a red line with pink coloring, that refers to its axis is on the right here. It's meters cubed per second in this particular case. And that is the annual value for the dry season minimum 5-day discharge for the time series, hydrological baseline time series from 1962 to 2012. So the 50-year time series that's been entered in meters cubed per second each year, that is showing you what dry season minimum 5-day discharge did. So in other words, in 1994, it was quite a wet dry season. So too in 2008. Whereas at the start of the sequence that you're looking at, 62 to 66, it was a relatively dry period in the hydrological record. The same refers here. This is wet season duration. In this case, it's in days, and it shows the duration of the wet season in each of these days. 1992, the wet season failed. The rains didn't come. The space below each of the graphs, here and here, these are the spaces to write your explanations. Okay. One of the most important aspects of drift is to get those explanations down. Sometimes, especially when they're filling in the curves, find it quite difficult to be writing all the explanations at the same time. They say, oh, we'll leave them for later and we'll get back to them to another stage. It doesn't work. Put in your explanations as you go for a couple of reasons. One, all of these different response curves and different indicators can make your eyes go screwy. It's quite difficult to keep everything in place. So it's good to write down your concepts. What we do when we're running an environmental flow assessment is that we will ask our specialists to write the stuff before we put them anywhere near a DSS. And the first thing they do is take their explanations so they know what their links are and what the explanations are. And the first thing they do when they get to a page like this is cut and paste the links from a Word document into here so that they're thinking, in the absence of the confusion of the DSS, of populating the DSS, is clear and is laid out here. Later on, you can come back and put in the references that are required and that sort of thing, but it's very important that your thinking is there. It keeps the specialist mind clear, and it also allows who's ever doing quality control to check the reasoning. We've had instances where people say, if the dry season minimum 5-day discharge goes down, the number of these fish will go up. And then when you look at the curve is saying if the dry season discharge goes down, the number of fish will go down. So you've got to be able to check that. So it's very important right at the outset to write the thinking down before you even start working with filling in the response curves. So once you have written your explanations, put your thinking down in that graph, it's time to start populating a response curve. So we go then to this little box here. This is dry season minimum 5-day discharge, and you're given 7 bits of information. So the first one, the most important one, is median. This is the median value for the linked indicator for the baseline time series. So in this particular case, the dry season minimum 5-day discharge median value is 20.145. The highest it's ever been is this thing called max base. So in the record that you're looking at, the maximum the dry season discharge has ever got to is 69.518. And the lowest it's ever been, from min base to baseline time series that you're working with, is 6. So from min base to max base covers the range of values in the baseline time series. Okay. Outside of that, you've also got 2 values. One is a min and one is a max. What these are values that are put in to capture the responses to scenarios that fall outside of what has ever been recorded, or what, to your knowledge, has ever been recorded in the system. Typically, if it's something like a 5-day minimum discharge or a duration or something, the lowest number will be 0. But that's not always appropriate. And on the other side, it's the maximum that you might expect this particular linked indicator to get to under one of your scenarios. So you need to know something about your scenarios and fill this in so that the specialist that's filling in this has some indication of what numbers they are focusing on. When the DSS has just been set up, these are default values. So typically, if it is something like a volume or a duration or whatever, the default value on the lower side will be 0. Sometimes that's not appropriate, most times it is. It's not appropriate, for example, for an onset calendar weeks, 0. Doesn't really work. Starts with week 1. And on the maximum side, the default is typically 15% above what the maximum in the baseline time series is. Any of these values can be changed manually if you need to later on. But this is what is provided at the outset, and by and large, we try to stick to that. The only thing that somebody who is running the environmental flow assessment may want to do is adjust that maximum value. If you adjust any values on this curve, they can all be changed, okay, quite easily. If you change any of them, you should remember at the start of the explanations to write that the x-axis is changed and the max equals 100. Okay, so that's the only one we changed. So you need to put a little note in there about what has and what hasn't changed on the axis. Okay, so those are the values that are coming through from your hydrological time series. So then what we do is we look at this portion of the table, and there's 2 values, y1 and y2. y1's got a whole lot of zeros that are entered there as default values when you start out, and y2 is empty. Essentially, what this is we work with y1 initially, and y2 is there if we need a bigger range of uncertainty. So I'll get back to y2 in a second. For now, let's focus on y1. One thing key to drift is the assumption that if you change just one part of the flow regime and you leave everything else the same. So right now, let's focus on y1. In order to fill in a response curve for a single indicator, you need to assume that only that indicator is changing. So only dry season minimum 5-day discharge is changing. Nothing else is changing. In other words, all the other aspects of the flow regime remain the same. The duration of the season, the onsets of the season, the characteristics of the wet season all remain the same. The only thing that's changing is the minimum 5-day discharge in the dry season. These values here need to be entered as drift severity scores. They'll be translated into percentages, but they need to be entered as drift severity scores. And in this regard, there's quite a handy little tool that's available on the website to help you get your mind calibrated for what might be likely to happen. And what this is just a whole lot of translations to help you switch between drift severity scores and percentages, and then the other way around, and to translate something like hydrological weeks to calendar weeks and months. Let's just find out what severities mean. If we enter a severity of 1, severities are on a scale of 1 to 5. If we enter a severity of 1, that means it's a 15% change. If we enter a severity of 5, it means it's 1,046% change. If we enter -1, it means it's 17% change, and if we enter -5, it means it's an 86% change. If you have a look here as I'm entering these numbers, what it is doing is it's providing you with a percentage change and a range of percentages. So the percentage change is the midpoint of a range. So -1 is giving 17.27, but the actual range is 14.55 to 20%. What that means is that if we go back to this page here on the drift habitat and biota page, if you enter a value of -1, then drift will use that 17.5. Okay, that's what they're going to use, 17.5, 17.27. So let's go back to drift. If you are thinking in percentages and you want to know what severity to enter, then you can enter your percentage here. Let's say we want 10% change, and it will tell you what severity you put in. So that's a plus 10% and that's a minus 10% change. It will tell you what the severity is that you should put in. So let's say we want a minus 10% change. So we put in a severity of 0.594. Let's just see what minus 0.594 will get us here. All right. So what minus 0.594 is going to do is that will be the midpoint, and then there's a range that is imposed around that. This is enforced by drift because we can never be absolutely certain of what our future predictions might be. We can say, yeah, it's fine, it's 10%, but in fact, we don't know. So what drift is going to do is it's going to say, okay, if my midpoint is 10.26, then I'll place a range over it. And the relationship that it's using to place the range is the one that's depicted here. So it's just, as you move further and further away from your median conditions, which is no change, so your uncertainty within your predictions will change as you go. So that's the default uncertainty that's put into drift. All right. Once you've decided on the percentage change and on the value that needs to go in there, into drift, on the severity value that accompanies that, if you go across to drift then and you enter it, let's just say it's minus 0.5. Let's call this up again. Minus 0.5, just to make it easier to keep on typing a whole lot of things. So that is going to assume that you mean 8.636. And it will assume that that's what you mean in all the calculations on the page that you see here. But drift will hold, in the background, will hold these other two values here. Okay, it will hold the other two values. And when you analyze your scenarios, at the same time as the DSS runs the analysis for all the median values, it also runs two other analyses, one for all the lowest points in the range and one for all the highest points in the range. And that's what enables it when you get the results. That's what the uncertainty limits that are shown, where they come from. They come from these ranges. Let's go to this page. So just to reiterate, if you're working on this page, it's going to work with the median values, provided you only have numbers entered in Y1. If, however, you want a wider range of values than the default values in the drift scoring system and in the DSS, then you can also enter a number in Y2. So let's just say here that we think that at a dry season minimum 5-day discharge of 13.077 cumex lower than the median value, We would expect that this fish would decline, but we don't know by how much it will decline. It will decline somewhere between minus 0.001, so a very, very small amount, and minus 5. There'll be a slight decline, but it could be 1% and it could be 100%. If you enter those two values, Drift will take the median position and it will calculate the minus 0.001 and the minus 0.5 as part of the lower and upper bounds data sets that it's calculating. But it will still show that information. So it will show the information in the response curve and it will show the information on the graph above. So you might ask yourself, well, how come then it's not showing such a wide range? And part of the reason is that you've got the minimum and the maximum clicked on. But it will show that range. Okay. For now, however, we are just going to work with Y1. Typically what you would do is get the specialist to fill in everything with Y1, and then having given a great deal of thought about the uncertainty and where you think things are moving for each of your linked indicators, you may want to go back in and increase your uncertainty in places. You can't reduce it, the default is there, but you may want to increase it in places. So let's leave Y2 for now. Okay, so let's just focus on fish species 1 for a second, and we need to fill in our response curve for dry season minimum 5-day discharge. Well, if the discharge goes down, you would expect the fish to decrease, and if it goes up, you would expect it to increase. It's a fish, it likes water. Okay, if the value goes to 0, what would we expect to happen to this fish? Well, this is minimum dry season discharge, so it's flow. If it goes to 0, it does not mean that there's no water in the river. And we said earlier that this fish managed to survive a whole year because it managed to survive in pools. So clearly, if in 1 year your flow goes to 0, your fish will not disappear. All right? Let's say that there will still be pools if there's not flow for that year, so the fish are not going to be eliminated from the system, but they'll be severely prejudiced. Let's say there'll be 20% of the fish left in the system. They'll have a hard time all being kept into it. So it's a minus 80% change. Okay, so we're looking at minus 0.475. All right. On the other end of the scale, what happens if the minimum 5-day dry season discharge goes up from 20 to 100. So it's 5 times more than it was. There's a lot more water. Do we think the fish will be doing a lot better? There's a lot more Lebensraum, there's more food, everything's doing really nicely. Okay, so we can expect that the fish will do better. I don't know how much better they'll do. That's up to the specialist to decide. But for the purposes of what we want to do, let's say that they will do 200% better. So we're looking at something that is, 3.47. Okay. So those are your two outer limits. Your median value, by definition, must remain 0. Drift considers that under median conditions, you're not going to get any major changes in your populations because that's what the populations have adapted to. So that will remain 0. So now what we have to do is just fill in these 4 here. We filled in our outer limits. We know our midpoint is 0. We need to fill in the other 2. If your median value was 20 QMEX and you've dropped 7 QMEX, it's not a huge drop. You need to look at your habitat, see whether there's stuff still available for the fish to be swimming around in, whether they're fairly well. But typically what will happen is it'll be a relatively small change because it's well within the realms of what happens year on year. And they don't tend to be very big changes in a system. So let's say it's a 5% change. Minus 5, minus 5. So we're looking at a change here of minus 0.297. And on the other side, if the flows double, do you think we'll get double the number of fish? Well, probably not. It's not going to increase by 100%. In fact, that's what we had. The other side there, so let's say we get a 20% increase. 1.41. Okay, oopsie, 1.41. And then we need to go through a reasoning to figure out what the initial values are for these other ones. I'm just going to put them about midway between the values that we've got there, and this will be 2. Okay. So what you've got now is a response curve and your explanation for why you think the response curve is that shape. First of all, why it is the fish get more when there's more dry season flow and less when there's less dry season flow. And then the details of that shape. What this is giving you here is an idea of how this response curve is driving the change, this blue, the change in fish species 1 year on year. It's important just to note the scales here because it only goes between minus 20 and 20%, so it's not the full range. So sometimes you think, ooh, it's huge changes, but it's not the full range. The important thing is what's happening up here. Now, what is happening up here is an integration of all of the response curves. At the moment, there's only one set of data that are filled in for the 5-day minimum, 5-day discharge, but the wet season duration would also be integrated once it comes in. And this is the one that's important. And you need to be asking yourself questions like, is it reasonable over this period that was fairly wet, had quite a long dry season, it had quite a long wet season, and a peak in the dry season, is it feasible that my fish population, we would expect it to go up by about 150%? You can zoom in on these and zoom out on these, and you can zoom in on these and zoom out on these to see what it is that you want to see. When you zoom in on these, it'll change the scale for you. Okay. Right, so let's just fill this one in very quickly. Median is 0. Wet season duration, if the wet season fails, well, that means breeding season fails, so you could expect our BC to be hammered quite a bit. I'm not going to get into huge amounts of detail about how much, but let's say it's a 20% reduction. So it would be a minus 1.18, and if the wet season continued all year, well, then you wouldn't have a dry season, so you can't expect it. But the fish will probably do quite well, but you can't expect it to do fantastically well. So let's make it a small number, 0.05. Okay, this is 0.002, 0.0111. This is quite close and that's quite far, so make that minus 0.1 and make that minus 0.5. Just see a bit of a line, and then it takes a dive at the end. Okay, and then we've got an explanation. Okay. So now we've got our data entered for 2 response curves. It's important to press save. So your initial data population is now done. All your explanations are entered and you can move forward with figuring out if you entered the right information. As I've said, the first thing to do is to look here and see whether the increases and decreases that are being suggested for the baseline are reasonable. Do you have any data for 1961 or 1987 or 2007-8 that show that fish increased over this time? Or do you happen to know that they didn't? So that's the point at which you really have to delve into specialist knowledge. But the DSS will do 1 or 2 things to help you. One of the things it will do is it will help you because it allows you to look at different scenarios to see what would have happened. With this response curve in place, what will happen? So you can go here where it says additional scenario and click any of your other scenarios. Typically what we do to calibrate a curve is that we'll pick scenarios that are, for instance, a repeat of the driest year on record. And ask ourselves, if this dry year continued for 50 years, would we expect this fish to still survive? Do our response curves let it still survive? Similarly, if we take the wettest year on record and repeat it for 50 years, will it just keep on going up, or does it reach some kind of a plateau given the response curves that we have entered? All of that is the stuff of the knowledge capture workshop. It's the stuff of this discussion. We've had projects where we've had the political people in countries sit and debate the curves. because in some instances it's more important that people agree on the curves and whether the curves are actually right. But whatever process you're adopting, this now gives you the basics with which to work. Of course, in a more real-life situation, you're working with a far bigger set of information, and in some cases here for species 2, you're linked to other sites. So if you've got migratory species, then you would expect to be linking to a different site, because if you have something that migrates from site 1 to site R, and the conditions at site R are terrible, so there's no fish to migrate back, it will affect your population at site 1 or site 2, whichever site you happen to be at. But by and large, what we've covered here gives you the basics to get started.